today you guys are making posters about Newton's first, second, and third laws. You all have read a little bit about a certain law. And then you also took notes on these 7 different items. All 7 items are going to show up on your poster. So come grab a piece of poster paper, put Newton's first law, second law, third law on top. Wait, don't go yet. And then underneath it, put your headline that you are going to, so each of you should have come up with a headline, try and agree on what headline goes next. And then start doing your examples and all the other pieces that go there. The poster needs to be done by the end of the period. It should be something that represents something about the law. So what law are you guys doing? Tell me about that law. What is that law? What's that all about? That's fine.
It's about like how forces act upon on each other, like how there's an equal force for everything, and then motion, about motion and stuff.
For example, if you throw a tennis ball at a wall, and it comes back as hard.
So tell me how that's an example of Newton's law.
Because
if you step on down, then the ground will push back, making you walk.
If you push down and the ground didn't push back as powerful as you did, then you would fall through the ground. And if it pushed more powerful, then you go way out or something like that. And just like they said, what it says right here, action equals reaction. So that just means just how they were saying it has to be an equal force. So you won't go smash into the ground or swing it up. Or when the tennis ball comes back as far as you come, whatever you do, the other side or the other force reacts to the same thing you did. So it can be equal.
So what if I'm not doing anything?
Gravity. The gravitation.
Oh, you mean I'm still doing that?
Well,
If I'm just standing
if
here?
you
Are
stand
there...
the ground isn't pushing force, the ground isn't as strong as can't hold you up, and you'll just fall right down. So it's all about gravity. If the force that's holding you up isn't as strong as the force that's pushing you down, then you'll just fall through.
But what about if I'm still standing here?
there's gravity acting
Are
on you.
there any forces acting on
Yeah,
me?
there's gravity acting on you, which is pushing you down, and then the ground is pushing upwards with the same force, and it's holding you up and canceling out gravity. So you're in a normal force. So the
Normal force.
Yeah.
What does that mean?
So just like we did with the bricks, the brick was on the table and it's in a normal force because it's not moving just like you are. And then since there's with the gravitational area on the world that makes you stay on the ground, but with the force of it's the force of the weight that makes you the weight of the ground that makes you jump not fall through it. So it's normal. So you don't have to be walking or anything, but there's still forces going on around you.
So if it's not normal, what is it?
There's normal force happens throughout everything, but there's also pulling force and if you're walking, that might be creating friction because you're pushing off the ground when you're walking and when you're walking.
No, go ahead. We're talking about friction.
Yeah, when you're walking with friction, you push against the ground. I think you push with more force or something, and that makes you go forwards. Not possible.
What do you guys think? What's interacting? What part of you is interacting? So is there a difference in whether I'm wearing... You guys notice how slippery it is out there? If anybody slid down the hall.
Or socks.
I was sliding down the hall and I was
Take your shoes off and slide down the hall.
Slide.
So tell me about socks versus shoes.
Shoes have more grip.
Yeah, they have like traction on the bottom, which forces it to like.
So tell me about traction and interactions between interactions.
Like when you, like as he was saying, when you have traction, like I think like just like with shoes, you're creating more friction, which is interacting with the ground. That the force of
Don't worry about the word. Just tell me.
it's like how like the force of the ground is helping you walk basically. That's what like I'm trying to say because the force of the so how like the weight force how so you won't go falling in. You're with all your like not with all your weight but with your weight you're pushing to walk to create more when you're creating more friction but like when you're sliding you're not really pushing. You kind of
Sliding.
when you're sliding you're pushing from your feet.
But what's the difference between being in socks and shoes?
When you're in shoes, you have rubber soles, and rubber creates a lot of friction with this kind of ground. So, like you get grip and there's friction working against you from sliding. But if you have socks on, then the socks are really slippery on this kind of ground because they don't create that much friction. So you can go sliding.
So where's the different forces there? Tell me that in Newton's third law. So what's Newton's third law again?
It is like
Yeah?
when one person is pushing or pulling, the other side is doing the same. I mean, but it's still applying the same force in the opposite direction. And yeah, I think that's the
Okay. So every time there's a force, you're saying there's a force in the opposite direction?
yeah. Just like when it says right here, when they push against the wall is pushing back
Okay.
because it's like this, like
So what's going on when you're running down the hall and sliding down the hall? Where's the action and where's the reaction? Why don't you guys think about that one and then maybe use that one as your example for number 3. And you guys can talk about how that's an example of.
your feet or shoes are pushing. You're pushing. If you overcome the friction, then you will go forwards.
It's kind of like when it was like sliding, people had chains on their tires. Like when they had chains on the tires, they had more traction, so they wouldn't slide. It's like that. So yeah, they still slid, but
It was a better chance of not sliding into the ground into ice.
Wait, where's my packet?
Each feet has inertia.
I have inertia. You have inertia?
So if you overcome your inertia, it results in acceleration. So if I start walking, then I
Okay, so you just told me what happens. What is inertia?
hey, Jaden.
Tell me how to overcome it. What is it? Okay, so you guys, I want to hear you all talking about inertia. So let's join in and see if we can come up with the definition.
Inertia is like a balance.
Something moving in a straight line and then like touch it and it's out of line. Inertia is happening because it's moving out of order. It was about moving.
So inertia is out of
Yeah, and that it goes naturally, but that it won't out of the pocket.
so there's a change of some kind. Okay, so what does that mean? It's a resistance
So like
change.
so like something's moving in a straight line or in a circle or like it's not moving out or anything, like it's moving in a straight line equals 4, 7 equals 9, 8 equals this way, or that way. So the formula is that, and then like you touch it or like move it out, inertia is happening because you're taking it out of the course.
So what do you guys think? You were thinking of it slightly differently. So you started with an object that was moving and then talked about what it takes to get it to move in a different direction. You were talking about starting at rest and then moving. So is this the same thing?
Yeah, basically kind of the same thing.
Well, first you say, over here, so like that, I have to say, it's a different way, but
Why is inertia important?
no one knows the law.
Tell me what Newton's first law is.
Object that rest tends to stay at rest.
Every object continues in the state of rest or uniform motion, straight line, unless it is compelled to change by that state by the first impress on it, upon it.
What's an example? Did you guys write down your example?
Yeah, I got a Sharpie. I just drew the ball thing.
Tell me what's going on here.
My turn. Well, like the rubber mats and the both like the same distance as it was on this side, but if like one side of the mat was open, it would go on like in a straight line. See, I got that.
Okay, I got it. So the ball, if there wasn't any inertia, the ball would just keep on going in a straight line if there was nothing in the way. And so, since there is inertia, the ball starts to slow down, plus including gravity and stuff. Yeah, friction too.
So is inertia what starts it or what keeps it going?
It's what keeps it going, that keeps it going in one direction.
So is inertia, what is inertia?
It took like for hours.
And then he just gave up.
Forever.
What happens if you take regular roller skates, ice skates, and what would happen?
Okay, so let's take that example. Let's take it. That's a good one. Let's take it and let's use Newton's first law.
This thing, you know, we're like talking about that it's acting something like tension, like yeah. And then after that, I made up the idea of I think you can go faster on ice in a regular car than on just like regular stick because the ice is slippery and I should get back to that.
So let's think about Newton's first law and let's think about, do you guys want to do the ice skater or the car on ice? Car on ice. Car on ice is our example. So let's try and think about Newton's first law and try to explain what's going on with the car on ice.
That's how we know it's ready.
It's really cold out. So we got this car and it's starting up here. Talk to me about Newton's first law. What's the first part of his first law?
Of the net force.
Okay, that car is sitting right up there. Is it going anywhere? First part done. Right? An object at rest and stay at rest. It just sitting there at ice, right? All right. Second part.
An object in motion in motion and time off the speed in a straight line.
Okay, so now your car needs to get into motion. How are you going to get your car into motion? It's on ice.
Change gears and then
Okay, so maybe you're.
Oh yeah, I forgot like the mask and the car had chain on it.
Ooh, good question.
Tire had
Good question. Hold on to that for just a minute.
because then it
Let's-
can move.
Oh, you're saying that it won't move at first
If it has no
if it has no chain.
Yeah, but it depends. Like it also depends on how thick the ice is.
How thick the ice is.
Yeah, like if the ice is like that much, then you put it higher than
Oh, why? Say why.
because the ice is like really high.
If it's too high, then what's the problem with it?
The tire won't move.
Why would the tire move if it were lower?
Like usually like ice is like slippery and it's like sometimes it's slippery and hard. Yeah, so like if it's up high, then like the person like they use the car and then like they try and then like when they go up it's slippery and it slips back down.
So did you guys understand her example? She says when it's really thick ice, it's, what were you saying?
It gets stuck in
Okay, the wheels just turn? Okay, but if it's really sort of just a little bit of ice, then what?
But if it's a little bit like that, you said you can also break the ice.
Oh yeah,
You can break the ice
Okay,
and
what
then
if that happens? Because then what if
because the car is way more than the ice.
okay, so if it breaks the ice, then what does it do? What's it then interacting with?
Wait, where's the ice on?
What good question? The ground, the street.
So if the ice breaks on the street, it'll probably just be in pieces, and so it doesn't really make a difference. Unless it's like a
What
really big
she's
difference.
saying that in that situation, the car could get home.
Yeah.
Why?
Because the ice, if the ice breaks, then isn't really anything slippery that's stopping it. So we have to do. Really
Because the wheels, what are the wheels touching that? Okay, and so the wheel, and why do they move when they hit the road, but not?
yeah, she could write. You just got to speed it up. Okay, how fast under it would be different? The summary of this, I agree with Amy because like the ice is very good. Okay, and the summary of this, we all know a car moves more than ice. And the breaks through, I think the car can move because now it's interacting with the ground. Okay, and after it's interacting with the ground, the ice won't matter anymore. And the tires are like on the ground, so if the tires are on the ground, the ice between the tires are gonna break because the car is gonna go.
So what's the difference? Why is that wheel that's touching the ground moving versus if it's on ice? Why is that one just spinning?
What does it say? They're like more compatible, like the ground.
What do you mean compatible?
Like they're like I don't think it's so well for ice, whereas in the road it's like a little still going it easily. I know, but like cereal and more like like tires are made out of glue.
Is this sort of getting at where your example, is this getting to your example? Is this sounding like this is your example? Because didn't you have a rollerblader on ice and an ice skater on ice? So did you hear this, what she just said? She said, a picture of a hand pushing a brick. You know, it's saying that like you need force in order to accelerate. And my other one was like I had a brick, and on both sides there's force pulling,
but it still is stayed at 0 with like the 2 equal forces. Why would
Oh my god, that's what I did. Ask Amy.
because they're like both pulling the same yeah.
What's Newton's second law? How can that help us explain that? Tell me what Newton's second law is. Oh my god! Okay, we are talking about.
When you summarize it, they said it was acceleration. It was not force divided by mass.
So what does that mean to you?
In like order to accelerate, you need net force, and in order to accelerate, the amount of force given depends on the mass of the object. Because like you'll need more force if your mass is bigger, and so in order to accelerate, you need more force because your object is bigger than just like something small where you can just use a little force and then it'll accelerate.
So sort of like trying to push this versus trying to push the table across the room. You're saying I need more, what? To move the table? I need to exert more force to move the table than I do. Okay. So this law can help explain that. What else can this law help Talk to me about something like acceleration.
I'm gonna write my name on it.
Is there an example here to talk about something accelerating?
Wait, like the brick?
But is it accelerating at a constant speed?
Oh, have your hands on the ground, but just like I learned to like your whole body flip.
What's another object that you guys think about that is a car? So let's do a car instead of a brick.
That's what I had.
Oh, is that what you had? Great. So what did you have about the car? It basically gave you that. What did you say about the car? It needs more force to get going? Yeah. Okay, so a big heavy car, a big Hummer versus a smart car. You guys seen this little one?
Yeah.
Which one is, it's going to talk to me about the difference?
The small car needs less force to move or accelerate, and the Hummer you need more force to make it move or accelerate.
Okay, so now say that those two cars are going down a hill. Which car is going to go faster down the hill?
The Hummer, the big car. The gravity and the mass of the cars.
So is gravity different between the Hummer and the smart car?
Gravity is the same, but just it's the mass.
So gravity adds more?
Not gas, but like
Okay.
it's bigger. It's gonna like go into the force.
She said there's no points for
It's gonna go farther. Maybe faster. It's like a bowling ball against a golf ball. Like if you drop them at the same time, the bowling ball will just go faster with the gravity.
Yeah, kind of like, because like this like example here, because there's like two people like falling in the air, but like the heavier one is going to like they have more weight, so like it's gonna go down quicker than
You're saying this one's going to accelerate more than this one.
Yeah, because like
gonna be like
the weight, sure.
like the weight from the person. Okay, so like pretend the air is pushing up. That's like one force, right? But like the weight is also like okay, so like pretend there's like I don't know how to do
This could be your example. Let's use this one as your example on the picture.
the air could be like going upward, right? But like the weight is going down, and since the air, like when the parachute, like the air is like going in, but real fast it's coming out also, even though it's running still, because there's more weight hanging onto them. And then like if there's light, like there's not much weight going onto it, which the air is pulling. Like it has more, the air has more force than the thing that's coming down.
Things like crashing into each other.
Yeah, they're like
What's crashing into?
combined.
Like your weight's gonna go like it's gonna since you're like heavier, it's gonna go like through the air quicker. Like if air was going up, then your weight is gonna go against the air. And since there's gravity, you're automatically gonna be going down unless you're like in space. So like you're gonna pull down against, and if you're heavier, then you're gonna go down quicker.
It's like the air, this is the air, right? And this is the parachute. Like this is like the heavy.
Oh, this. Okay, the heavy parachuter.
Yeah, like this one right here, the air is just gonna come in. It's gonna like, there's like no more space for the air here. So it's gonna like the air that's coming up is gonna fight the air that's already in there to like make it out. Like the air that's already there, it's gonna like come down again and then like go up that way. But like the lightweight one will be like this, right? But like it'll just like goes like this, but then it'll take a little bit longer than this one to come out. But then it'll do the same. It has the same procedure, but like just this one's slower than this one
Tell me why.
because this one has less weight than this one.
Can you use arrows?
So like, okay, this is the parachute, and then like the air, the weight force is coming down, but the air is like this way, taking slower to come up. So the air is taking more time to fill in the parachute. Like,
They're not going as fast.
yeah, they're not. It's not as the same mass.
So I want you to draw these two parachuters over here, and then I want you to use the same arrows that you were just talking about, and think about. So now you're now talking about there's a difference in mass. And you're saying is there a difference in acceleration for the two parachuters?
Yeah. One's accelerating fast.
Is there a difference in force?
Yeah.
Think about that. Draw your pictures and draw that one as an example.
Yeah, there's a lot to go. One person is like bigger.
Oh yeah, and the force is like flowing down, and then that force is like going against the same force.
Yeah, on this thing, but we have to finish our concept. We're gonna do like 7 things.
Our example is this kid, he kicks the wall, and the force comes, it's a super kick, and the force comes back, like really hard since he kicked it hard. He says, ouch, and then his friend says, stupid, think about the third law. And that's our example.
He's got a big kick.
That says E. And then the arrows represent the force. This arrow represents force from the kick. And then this arrow represents the force that comes back.
And we label it.
You're 6th graders just learning. I saw you with Bruce Lee.
Yeah, we did Bruce Lee.
Stretch his legs. So, and then the title, action is reaction.
Why do you say action is reaction?
Action. Yeah. Because basically it's the same thing. Because when I was looking up on here, because I wrote it down, it says right here, it says one force is called action and the other is reaction. And then right after it says it doesn't matter which force we call action and which force we call reaction. So we just said action is reaction.
So have you had a chance to talk about one of the last questions that Ms. Broughton asked you to think about was the roller skater? Yeah. So have you thought about this law and that example? Tell me about the action and reaction law on that.
When he's on wheels, because the wheels can roll, there's like very little friction, so you don't have to work that hard to overcome the friction and go hard. So it's really easy to roll in roller skates, but in your shoes, you have a lot more friction, so it's a lot harder to slide or anything.
So where are the two different forces there?
To roll, you have to push from the leg, and then the reaction is the feet pushing back on the wall, and the wall pushing back.
Pushing back where?
Pushing back at you.
The wall?
The ground.
Oh yeah.
Oh, the ground.
The reaction, I think, is the friction, and the action. I think the reaction is something working against them. And the reaction is the friction, and the action is them pushing. I think the action is the force of friction, and then the reaction is the pulling force, because like just like on the diagram, it's side by side to each other, just like the normal force and the weight and the force of gravity. Because the pulling force is like when they're pulling their legs back up. When they're skating, they're like pushing, which is the friction when they're pushing, and then when they're pulling the other foot forward, which is like when they're pulling it forward. I don't know if that's right, but that's what I think.
Well, maybe there's multiple examples of action versus reaction, because it seems like you're really talking about what's going on with the foot impacting the floor, and you're talking about the whole leg muscles and moving forward. So maybe there's a couple different things to think about. But this example takes us back to where we started with you guys sliding down the hall in your socks, right? So that's something I want you to think about for Saturday. Is how are we going to explain that, or the roller skater? What are the two different forces, opposite forces that are going on there?